Okay, this is our chapter 2 and topic 2. Topic 2 cover DC analysis of diode circuit. Okay, as we have discussed in previous part or previous topic, this is the current voltage characteristic, or we call it IV characteristic of a PN junction. So we have the current voltage characteristic. The y-axis is current and the x-axis is voltage. And then since we have the PN junction is a diode, so we assume this is the symbol of diode. So this is cathode. So we apply, in this case, we ground the cathode and then we apply a voltage here. We apply voltage at the anode of the diode. So when the voltage is in a positive value, so this is what we call it a forward bias. So this is forward bias. Forward bias means the condition where we apply the voltage to the diode that allow the current flow. So at the forward bias, the depletion region at the PN junction decrease gradually until certain point the depletion can be ignored, and then that's the point where the current start to have a sudden increase. So this is a forward bias. And then at the negative voltage, we call it reverse bias. Reverse bias. In a reverse bias, the depletion region become wider, and then this condition does not allow the current flow. So in ideal case, the current is zero. So that's why we have the current is zero at the negative voltage, and at the positive voltage, above certain point, the current start to flow. This is current voltage characteristic of a diode. Okay, so based on the IV characteristic of the diode can be classified as a non-linear device. So what is non-linear? Non-linear device means that the output current does not vary linearly with its output. So what is the example of a linear device? The simple example of a linear device is resistor. So resistor, we know that resistor, the voltage and the current relationship is expressed using the Ohm's law. So when we have the resistor, let's say resistor equal to V over I. So we have I equal to V over R. So the relationship between I and V is in a linear. So when we draw graph I versus voltage, current versus voltage, we should have a straight line. But in case of diode we don't get the straight line, we get a curve. So you get a curve, current voltage characteristic. So that's why we classify diode as a non-linear device. Okay, so the curve that is shown, the curve IV curve that's shown in the previous slide, actually can be expressed using exponential function of voltage Vd. So this is the mathematical expression of the current as a function of voltage. Okay, as a function of voltage. So we have here okay, so we have the IS. What is IS? IS is saturation current. This is a fixed value. The saturation current fixed value typically is very low. around femto ampere. And then we have this one is okay, actually this N, so this is this should be N. This is N. N is emission coefficient, so the value is around 1 to 2, depend on the material, but usually we put this is the N value is 1. And then we have the Vt is a thermal voltage. Thermal voltage depend on the temperature. So at the room temperature, Vt is equal to 25.9 millivolt or 0.259 volt. Okay, so this is the mathematical expression of the current diode. Okay, so next we will discuss on some important properties of the diode. Okay, first is a knee voltage. What is knee voltage? Knee voltage is when you consider a forward. When you consider a forward, this is a forward bias, because the voltage is positive. Okay, you can see the transition from the region where there is no current. So we have this is current is almost zero, and then this is the region where the current increase is very rapid. So the rapid increase of the current. So this is current is high. So this is the first region is current is 0, and then the resistance is infinity. Sorry, the resistance is infinity, but here the current is high, resistance is almost 0. So this is the two region. The knee voltage is actually the transition point. So the voltage where the current flow increase rapidly. So you see here, this is the region where the current increase rapidly, and then you can see actually this is the point where the transition from this the first region where the current is very low. So you start to have the transition to the next region where the current is very high and resistance is almost 0. So this is the knee voltage. So the knee voltage is around 0.7. Okay. So from this graph, we say that the knee voltage of this diode is 0.7 volt. So the actually the diode will which have knee voltage of 0.7 volt is a silicon diode. Okay, if it's a silicon diode, the knee voltage should be around 0.7 volt. So this is a common typical value for the knee voltage, acceptable value for the knee voltage. Okay, but if the diode or if the PN junction is made from the germanium, okay, you know germanium is another type of elemental semiconductor. So if the diode is made from the germanium, the knee voltage will be lesser, which is around 0.3 volt. Okay, so this is one of the things that need to be taken into account when you want to identify the PN junction or the diode, whether the diode is made from silicon or the diode made from germanium. Okay, so next we discuss on the diode resistance. Okay, so the diode does not have fixed resistance value because the IV characteristic is a non-linear characteristic. So the resistance keep changing depend on the operating point or the voltage point. So here we have three types of resistance. The first is the DC resistance, or we call it static or DC resistance. So DC resistance is simply using the Ohm's law. So RD is equal to VD over ID. Okay, and then the second type of resistance is we call it dynamic AC resistance. This is dynamic AC resistance. So when AC resistance means that we need to have a difference. We have to have a delta VD. Difference of delta VD over delta ID. This is equal to 20. This is if you consider this the exponential equation given in the previous slide, exponential equation of the diode current. So actually we can derive this equation. So at the end, the dynamic AC resistance of diode is equal to 26 millivolt over ID. So this is here the delta VD over delta ID. Okay, delta VD over delta ID can be solved by differentiating the exponential equation given in the previous slide. But here we will not discuss in detail about that. But at the end, the equation will be something like this. RD is equal to 26 millivolt over ID. Okay. And then the last type of resistance, we call it average AC resistance. Average AC resistance. So the third one is slightly different with the second one. Although this is delta VD over delta ID, but the difference is this is average. So what we do is we take the average of delta VD over delta ID from one point, PT stand to point, PT stand point, from one point to another point. So we have 2 points and then we get the average AC resistance. Okay, these three type of resistance can be depicted or can be shown in this graph. So let's say we have current versus voltage. So if you want to calculate RD, you want to calculate RD at this point. Let's say at this point, what you need to do is you get this ID value and you get the VD value, and you have the RD is equal to VD over ID. So this is the DC resistance. Okay, next is AC resistance, small RD. Okay, AC resistance is actually is delta VD over delta ID. Okay, delta VD over delta ID. Okay, in the mathematics, this when you have the function and then you do this you differentiate the equation, actually you get we call it a tangent line. This is a tangent line. So this line will have this one 90 degree of this 90 degree of the curve. So this is what we call it tangent line. So you get the tangent line and then you have delta VD and you have delta ID. From that you can get the small RD. This is in a mathematic approach. But because since we know the function is exponential function, we can do you can solve the differentiation part, and then last we can get 26 milli over volt over ID, as simple as that. Okay, and then last one is average AC resistance. Average AC resistance is calculated when you have 2 points. So we have between this point and this point. So you just simply get the delta ID, delta VD. Delta means the difference of value. So difference of this, let's say this one is ID1 and this one is ID2. So delta ID is delta ID1 minus delta ID2. Okay, this is example how you let's solve one example how you calculate DC and AC resistance as well as average AC resistance. So let's say you are given the current versus voltage characteristic. So this is the graph, and then this is the value. This is the value along this graph, this line. Okay, the question is you need to calculate DC resistance, AC resistance, and average resistance. Okay, DC resistance at VD equal to 0.73 volt. So RDC is equal to, okay, you look at the table here. Where is VD equal to 0.73? 0.73. We have two options, whether you use this one or you use this one. Let's say we use this one, use 0.729. Okay, we use this one. So the RDC is equal to, the V is 0.729 over ID. This is 0.00177. So when you calculate this one, okay, you take the calculator and then you will get the answer. Okay, let me calculate this one. 0.729 divided by 0.00177. Okay, so you get the answer is 411.86 ohm. So this is the DC resistance. Okay, next is AC resistance. AC resistance at VD is equal to 0.73. So this is quite straightforward because the AC resistance is given by this simple equation, 26 milli over ID. So the ID is 0.00177. So the answer is 26 over 0.00177 is equal to 1.77 milli. So 1.77. So the answer is 14.69 ohm. Okay, 14.69 ohm. And then last one, average AC resistance. Okay, average AC resistance, you are calculating using 2 points. So VD 0.7318. Okay, this one. And then VD is equal to 0.729. Okay, so this one, so so average AC resistance is delta VD over delta ID. So delta VD is you just the difference between these two voltage. So 0.7318 minus 0.7291, and then this is over the current difference. The current difference is, we have here 0.00197 minus 0.00177. Okay, you use your calculator and then you should get around 30.7 ohm. So this is how you calculate DC resistance, AC resistance, and average AC resistance. Okay, so some comment on the difference between DC resistance and AC resistance. Okay, AC resistance actually show the actual status, or actual what I mean by status is whether the diode is on or off. For example, if the point is at this point, so resistance of AC resistance will be close to infinity. But when the point is here, so the resistance, AC resistance is, let's say we call it, this is AC average, R average is almost infinity. But at this point, the R average is almost equal to 0. So the AC resistance actually indicate the whether the diode is on or off. Okay. So next we move to the part of the reverse bias. In the previous slide, we discussed on the properties of diode based on the forward bias characteristic. Okay. How about at the reverse bias? So we know that at the reverse bias of the diode, the ideal case, the current is 0. So the current is 0. Okay. So let's do some revision. Why the current is 0? Okay, the current is 0 because there is very small amount of current that can pass through the PN junction. Okay. So in actual PN junction, so this is the diagram show the PN junction at reverse bias. So we have the P type, this is the P junction, P type, PN junction, we have the P type, this is P type, and then this N type. So at the P type, we apply negative voltage, and then at N type, we apply positive voltage. So this is a reverse bias. So this is a reverse bias. At reverse bias, the depletion region become wider. So it become wider. So we cannot expect any current flow. Okay, the current flow. But however, when we do the measurement, we can still measure very small current, very small current. So why there is small current? This is because of the movement of minority carrier across the movement of minority carrier across the PN junction. So this is the reason of the current. So what is minority carrier? For the N type, minority carrier is electron. So we know the sorry, not N type. Okay, my mistake. This is P type. P type, the majority carrier is hole. P is positive. P is positive. The majority is hole. The minority is electron. So N type, the majority is electron. The minority is hole. So at the P type, so at the P type, we can still have a electron. Okay, although this electron is a minority. So we have the electron, but electron is very small number. So since we have the electron, the potential barrier or the built-in potential formed inside the depletion region will not impede the movement of the minority carrier. Okay, but rather it attract the electron to cross the PN junction. So we have this electron is negatively charged. So positively charged ion inside the depletion region will attract the electron, minority electron inside the P type to move across the PN junction and eventually will produce a very small current. Okay, since the number of electron is very low, so the current is very low. Okay, this is the graph. So if you take a look at the graph, the value of the diode current at VD is equal to negative 0.6 volt. So we have the value is around 10 power of minus 15 ampere. So it's very low. Okay. So in ideal, this is zero reverse current, but now we have 10 minus 15 ampere. Okay, almost equal to 0. Okay, in ideal case, the reverse resistance should be infinity because 0 reverse current. So now we can calculate the reverse DC resistance by simply divide the voltage over current. So minus 0.6 over 1 times 10 power of minus 15 is equal to 6 times 10 power of 14 ohm. So this is very high, so almost equal to infinity. Okay, in a reverse bias, in the previous slide, we apply around less than 1 volt, less than negative 1 volt. What if we apply a very high reverse bias? Let's say negative 100 volt. What will happen? Okay, when we increase the reverse bias up to 100 volt, what will happen is the minority carrier, which is electron inside the p type, will gain very high energy. They will have very high energy, and with that with such energy, the electron can produce more electron. So minority electron with high energy can produce more electron through a collision process with the silicon atom. Okay, if you can recall our discussion on why we have the free electron inside the silicon semiconductor, this is because there is external energy. For example, the heat energy from the temperature, which can release the electron inside the atom. But here in this case, when the external or free electron have high energy, the electron will collide with this atom, and then the collision, the process will result in or produce more electron. The electron inside the silicon will be released after the collision. Okay, so and then there will be more electron. When there is more electron, the newly generated electron will also gain high energy because we apply a very high reverse bias. So this process is repeated and lead to the multiplication of electron. Means that the number of electron become greater in a very fast pace. So this is a sudden increase of the current. So this process we call it avalanche. So this is the image of avalanche. This is the avalanche happen in the snow mountain. So maybe at the tip of the mountain there is the starting size of the snowball is just small, but along the movement from the top to the bottom of the mountain, there will be the accumulation. So the size of the snowball become bigger, and then at the end it's become big. So this is what we call the avalanche. So the avalanche is referred as a breakdown of the diode. Means that the diode is not in a normal operation. So breakdown is means that it's not normal. Okay. Okay, breakdown is a current through a diode in reverse direction increase rapidly once breakdown has occurred. So usually in a reverse bias, we want to have a zero current. So this is normal operation. But now, when the apply bias is very high, so we have the breakdown. So this is not normal. Okay, the breakdown voltage, or the point where the current start to increase at the reverse bias, we call it breakdown voltage. The breakdown voltage depend on several factors, and one of them is a doping level inside the PN junction. So for a a certain diode, the breakdown voltage might be different from the another diode. This is depend on the characteristic or the specification of the PN junction. Okay, remember that the breakdown voltage means that the diode cannot be used. Means that the diode has been damaged. There is possible damage inside the diode. Okay, so now we have the complete IV characteristic of diode. So you see here, this is fault bias. So fault bias usually positive voltage. So below than barrier potential, or we call it a knee voltage. Here, this is knee voltage. Have knee voltage. So in case of silicon, this is 0.7 volt. Below than knee voltage, the current is very low. So the current is almost zero. But above the knee voltage, the current is high. And then the resistance is almost zero. The resistance of AC resistance at the on state here is almost zero. At the reverse current, at reverse bias, the current is also almost equal to 0 volt. But when we apply much higher reverse voltage, we will come to one point where there is a breakdown. So the breakdown, when the breakdown happen, the current start to flow. So this is what we call it. This is the point we call it breakdown voltage.